All right, 10.3, let's get at it. Chord arc and diameter. So you've already been shown what those three things are. Those are the most important things. We're going to be talking about those and what diameters do to all that stuff. So let's hit the theorems and get them out of the way. In the same circle, congruent corresponding chords and theorem. In the same circle. Two minor arcs are congruent if and only if their corresponding chords are congruent. Okay, so what that says is if you have these two arcs right here, this chord, this chord and this chord, if those two are congruent, and that's what that says, then you know that the arc of both of those are congruent to each other. Okay, because they're not all going to be marked. One of them will be marked and one of them won't be. But you need to remember that theorem. Any questions on that? Okay, good. So we're going to start getting into lengths of things and being able to calculate this stuff. All right, let's go to the next. Perpendicular chord bisector theorem. So this is a big deal. We're going to sit here on the diameter for a little bit. If a diameter of a circle is perpendicular to a chord, perpendicular means 90 degrees. Okay, then the diameter bisects the chord and its arc. Okay, so that means HD is congruent to HF, and the arc GD is congruent to the arc GF. That's what that means. Got it? Yes or no? Basically what they're going to be doing is they're going to use some algebra. They'll say, hey, this piece equals this and this equals this. How do you know what x is? And you got to set them equal to each other and find them. Okay? But we'll go through and do these extra practices, all right? But the point is, if the diameter bisects that chord, then you know the arcs are congruent to each other. Look down at the bottom on 10.8, perpendicular chord bisector converse. If you are shown that the chord has been bisected, yes.
Are you writing on this?
Yes, can you not see that? How's that? Yeah, you need to come sit up here. Okay, so if TP is marked as being congruent to, let me use a different color here, to PR, okay, if those two are congruent to each other, then you know that the arcs are congruent, okay? And that means that SQ must be a diameter. All right, so there's nothing there that shows that SQ is a diameter. But now that you have that TP and PR are congruent to each other, then that tells you that it has to be a diameter. So if you got this line that goes through and hits this chord, if you can show that this piece is equal to that piece, then you have a diameter. If you can't prove that these two pieces are congruent to each other, then you don't have a diameter. That's the whole point of this, all right? All right, next. Right now we're just going through the theorems, and we'll talk about how to do this, all right? In the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. Okay, so again, look at the two pieces from the center. GE, I'm going to blow this up. If GE is congruent to EF, okay, then you have AB is congruent to CD. If AB is congruent to CD, then EF is congruent to EG. So they're saying, if you know these two chords are congruent, then these two pieces have to be congruent, and they're perpendicular. All right, next. And we need to practice them. Here we go. Find the measures of the arc or chord in circle Q. So we want WX. We want this right here. Everybody see that? So to find WX, what do you think it might be and why? Anybody want to guess? Now remember, this is an arc, so we need a degree. So we don't want to say that it's 3.6. 3.6 is that straight line there. So an arc is definitely longer than that straight line. No guesses about what that degree is? Yes, Cameron. Why do you think it's 42? Okay, so what we have here are two lines that make vertical angles. Okay, so therefore this is 42 degrees, which means its arc is 42 degrees. Oh, I can't see that. So, I said 45, that's 42. Okay, this is a central angle from the center. So the arc and the angle made are the same. Okay, so that's 42 degrees, not 45. Let me erase that and give you a better one. Okay. Now, YZ is next. And we're not talking about the arc, we're talking about this line right here, YZ. 3.6. Emily, why is it 3.6? Yeah. Yeah, so since those angles are the same, then those chords are going to be the same. Since the arc is the same, the line attaching them have to be the same. So if this arc, WX, is the same as YZ, because of 42 degrees here, central angles, then the segment that connects them, these are chords, and these chords are the same. Which one is it? I don't remember which one it is. So if the arcs are the same, then the chords are the same. It should be one of the first ones. All right, WZ. So now we're going W to Z. How do you think we're going to figure out what that angle is? Remember, an arc is a degree for now. Okay, watch. So this is a straight line right here. So X to Z is a straight line. Everybody agree? What? It's going through the center of the semicircle. That's right, which means this is 180 degrees. If that's 180 degrees, how do I get WQZ? How do I get this angle right here? Remember, it's a half a circle. How many degrees is a half a circle? 180 minus the 42. Isn't a straight line 180 degrees? Yeah, so take 180 minus that 42, and you get 138. 138 degrees for that central angle, which means the arc is 138 degrees. Are you guys writing those down, those answers? So the arc is 138 degrees. I guess they weren't asking for the arc, were they? Okay, they wanted the line. So sorry about that. So what's WZ then? This right here. Everybody said it? What is it? 9.2, guys. 9.2. It's a rectangle. And if their arcs are the same, and we can show that the other arc is 138 degrees as well, then that means those sides are the same. All right, what's that last one? Arc XY. Okay, which we just did WZ. And since those segments are the same, then this side is 138 degrees as well. All right, remember, you got to subtract from 180 if you have a semicircle. Subtract those angles that you have. All right, let's move on. Let's go down to the next one. Find the value of X. Okay, now we're getting into some of these other theorems that we had. So, you have a diameter here. It's a chord that goes through the center. It's called a diameter. It's hitting this chord at 90 degrees. Which means what to those two segments that are made? They're equal. So PT is equal to TR. So we take 2x minus 4.1 and set it equal to x minus 0.5. Everybody take a second and solve that. Jake, what's my first thing I should do?
Put 2x minus 4.1 equals x minus.
What's the next step?
Then you combine my terms with the x's.
Yeah, we're gonna move. I'm gonna move that x to the other side. You could have moved 2x to the right side. I like my x's on the left, so I'm gonna subtract the x to the left. Rewrite the whole thing again. That negative doesn't, the minus sign doesn't fall away. That seems to be a typical mistake. Don't forget, the minus sign never falls off. Who can tell me the next step? Riley? Yeah, we gotta move the 4.1 over. Good job. But are we adding or subtracting? I'm gonna add it because it's the opposite of what we have there. Okay. Now the question is, what's that answer? Yeah, good job, Jody. 3.6. Okay, if x is not 3.6, then this is not drawn right for a circle, but we had to find the value of x that makes this true. Okay? All right, let's do another one. Sorry. We have another one here, don't we? What the heck is that? Okay. Same thing. What do we do? Yep, set them equal to each other and solve. So everybody do that. I'm going to pause this, give everybody a chance to finish it. Okay. Let's see here. I'm going to move the 2x to the left just because that's what I like to do by subtracting it. So that's x minus 5 equals positive 1 on the right. Okay, and then I'm going to move the minus 5 to the right by adding it. And x equals 6. How's that? Who got 6? Raise your hand. Okay, I know some of you were struggling through that, made a little error. All right, let's go to the next. Oops. Find the radius of the circle. Wow, how are we going to find the radius of the circle? There's no radius up there, is there? How about this? There's a radius, isn't it? All right, so we got to find r somehow. First of all, what do you want to do when you just look at this problem? Yeah, solve for x. And what do you guess we would do to solve for x? Okay, now there's a theorem that we learned that if these two pieces are equal to each other, BP and PE, if they're equal to each other, then we know those two chords have to be equal to each other if they're perpendicular, okay? So AC is equal to DF because you have perpendicular lines coming from the center and they're the same length, okay? So go ahead and let's solve that. Everybody knows how to do that. Let's set it up. 5x minus 2 is equal to 3x plus 2. Everybody solve that. All right, so again, I'm going to move the 3x to the left. Guys, that's just typical to move your variables to your left. You always don't have to. So 2x minus 2 equals a positive 2. And I'm going to move the minus 2 to the right by adding it. So 2x equals 4. And then we divide the 2 off of that. And x equals 2. But you're not done. It didn't ask what x was. It asked what the radius was. So if x is 2, I can plug it back in there and get 3 times 2 plus 2. 6 plus 2 is 8. So the chord DF and the chord CA are both 8 units long. Which means DE is 4. Okay? So the whole thing is 8. This is 4 right here. This splits this into 2 pieces. Okay? This is perpendicular. It has to be perpendicular. If it's not perpendicular, it doesn't work. Okay? Because if I had this chord going from here all the way over there, it definitely wouldn't be split in half, would it? Okay? Do y'all see that? So if I have a line coming here and I hit this chord, this little piece here is not the same as that piece. So the key here is that this is perpendicular. Okay? So if this is 8, that splits this into 4, and now we have a right triangle. And to get the hypotenuse of a right triangle, what do? What do we use? Chapter 9, section 1. Pythagorean theorem. So there's your A and there's your B, and we need our C, right? A squared plus B squared equals C squared. So 3 squared plus 4 squared, everybody solve that please, equals the R squared. Jody, what'd you get? 9 plus 16 equals R squared. 25 equals R squared, and you all learned to take the square root to get rid of a square. So the radius is 5. You had to do all that work just to find the radius. So guess what? Everybody do number 8. Let's see if you can get it right. It's a little bit different, but you do the exact same type of thing that we've been doing. All right. Set 4x minus 5 equal to the x plus 4. And I'll subtract the x. 3x minus 5 is equal to 4. Add the 5. 3x equals 9. And divide off the 3. X equals 3. So that's 3 and that's 3. And again, this whole thing is 20. Wx is 20. I could have used the other one. So that means this little piece is 10. And I need the radius. So now we use the Pythagorean theorem again. So hopefully you got 3 for x. If not, go ahead and change that and let's move on. So we got 3 squared plus 10 squared is equal to the radius squared.
Wouldn't you do x plus 4?
Oh yeah, thank you. Thank you. I made a mistake. First mistake all year. All right, so yeah, if x is 3, sorry. If x is 3, then this is 7. Thank you for catching that. All right, so let's redo this piece here. 7 squared plus 10 squared equals r squared. Does that look better? All right, so 49 plus 100 is equal to r squared. So we need to take the square root of 149. And let's take a look at that. Square root of 149 is 12.2. Who got 12.2? All right, that's it for that. 10.3. We got a homework check tomorrow.